Hi and welcome back. Welcome to section 4.3, derivatives and shapes of curves. First and foremost, super important. If a function is increasing on an interval, well, what can you tell me about its derivatives? Well, let's take a look at this graph from down here. From about this point to this point between these two x values, the curve is increasing. So if you are at any point on this curve, the slope of the tangent lines is going to be positive. And the slope of the tangent line is also the derivative at that point. So a function is increasing on an interval, then the derivative is positive on that interval. Wherever a function is decreasing, so to the left of this point, so this is increasing, let's write that down. So f is increasing, so its derivatives are positive between those 2 points. If you go to the right of this point in this particular curve, if you're at any point on this curve, your tangent lines are going to have negative slopes. So the derivative is negative. So where f is decreasing, the derivative is negative. So if f is decreasing on an interval, then the derivative is negative on that interval. So for this particular curve, the function's increasing between these 2 points. Thus, between these 2 points, the derivatives are positive. To the right of that point, the function's decreasing, so the derivative is negative. And likewise, to the left of this point, if you're at any point on this curve, your tangent lines are going to have negative slopes. So f is decreasing here also. So the derivatives are also negative to the left of that point. All right, so we want to be able to determine where a function is increasing or decreasing, not just by eyeballing it, but by using calculus. So let's use calculus to find the precise locations of increasing and decreasing for this quadratic function. All right, so what we do is, we'll notice where a function changes from decreasing to increasing, there's a local min, or a function changes from increasing to decreasing, we have a local max. So our goal is to first find all critical numbers. Find all critical numbers for f. So we're going to take the derivative, 6x minus 2, and 6x minus 2 equals 0 when x is equal to 1/3. So add 2 divided by 6. 6x minus 2 is not undefined anywhere. It's a linear function, so this is the only critical number. This is the only critical number. So we're going to test the behavior of the derivative before and after the critical number. Because how the derivative behaves to the right and the left of this critical number determines how the original function behaves. So what I like to do is I draw a number line. There's different ways to do this. I put my critical number on the number line. It doesn't matter where you put it. I tend to put it in the middle if there's only one. Right? And you're going to pick any number to the left of this critical point. And you're going to test the derivative. And then you're going to tell me something about the original function. So let's look. f prime of x is equal to 6x minus 2. So I pick any number to the left of 1/3, let's just say 0. And if you plug 0 into the derivative, f prime of 0 is equal to negative 2. So the derivative to the left of 1/3 is negative. I promise you that if you pick any number to the left 1/3, the derivative is going to behave exactly the same. The only place the derivative could possibly change from negative to positive is at 1/3. So it's either entirely negative or entirely positive to the left of 1/3. So I picked the simplest number to the left of 1/3, which was 0, plugged it into the derivative, and saw that we got a negative output. So the derivative is negative to the left of 1/3. So the original function is decreasing to the left of 1/3. And then I pick any number to the right. So here I pick 0. I picked any number I want to the right of 1/3. 1 seems to make sense. Easiest number to plug into this function. We put 1 into the derivative, and the output is 4. So any number I pick, you can try 9/10, you can do 700. Any number to the right of 1/3 is going to produce the same result for the derivative. So the derivative is positive to the right of 1/3, so the original function is increasing to the right of 1/3. So f is decreasing on. We say, well, to the left of 1/3 would be negative infinity to 1/3, and it's increasing on 1/3 to infinity. Notice neither intervals contain the value 1/3, because at 1/3 it's neither increasing or decreasing. The derivative is 0, so it's a critical number. All right, let's take a look at what these graphs look like. Here's the graph of the original function, y equals 3x squared minus 2x plus 4. And here's the graph of the derivative, y prime equals 6x minus 2. So the function's decreasing until about right here. We found the precise location of that point. It is at 1/3. So remember, we want to use calculus to find the exact value. We don't want to look at a graph and say, oh, it's about this. It's exactly at 1/3. We could find the local minimum value by plugging it into the function. We can see that the function is increasing to the right of 1/3. And we can see if we're anywhere in the curve to the left of 1/3, the function is decreasing. Now, graphically, how does that relate to the derivative? Here's the derivative. Notice the derivative is 0 at 1/3. If I just look at both the function and the derivative to the right of 1/3, where the function is increasing, the derivative is positive. Notice the derivative falls above the x-axis, where the original function is increasing. If I look over here, where the original function is decreasing to the left of 1/3, the derivative falls completely below the x-axis. So from here over to the left of 1/3, the derivative is negative. That's not a coincidence. That's always going to be the relationship between a function's graph and its derivative. All right, so let's sum this all up. What we just did was called the first derivative test for increasing and decreasing in local max and mins. So the first derivative test helps us find the exact location. Again, this is using calculus, not your calculator. So we find the critical numbers for f. So f prime of c equals 0, or f prime of c is undefined. The critical numbers for any function is where the derivative is 0 or undefined. You look at a number line or create a table. If the derivative changes from positive to negative at c, then f has a local maximum at c, and f changes from increasing to decreasing at c. Now we always read left to right, so if the derivative changes from positive to negative at c, it goes up, hits c, and then it goes down. So it's going to be a local maximum. The function changes from increasing to decreasing. If the derivative changes from negative to positive at c, then f has a local minimum at c, and f changes from decreasing to increasing at c. So if the derivative is negative and you go left to right, if the function's going down, hit c, and then the derivatives start becoming positive, the function goes from decreasing to increasing. If the derivative does not change signs at c, then c is neither a local max or min, and f does not change directions at c. All right, let's try another one. Let's find all the local extreme points for this function and determine the intervals of increase and decrease. All Okay, so we're going to take the derivative and find all the critical numbers. The derivative is 6x squared minus 6x minus 72. I'm going to set the derivative equal to 0. I'm going to factor the 6 out and see if that helps. X squared minus x minus 12. Yep, that helps greatly. 6. We're going to factor. You could use the quadratic formula. You would get the same result. This is just a lot quicker and easier if you're good with your factoring skills. So we get 4 and negative 3. So therefore, my critical numbers are 4 and negative 3. Now I'm going to look at the derivative before, between, and after. Right, so we're going to have my derivative, which is f of x is equal to 6x squared minus 6x minus 72, which is also equal to 6x minus 4, x plus 3. I'm just writing it so it's right close to our number line right here. Left to right, negative 3 comes first, and then 4. So this function behaves the same to the left of negative 3, and then it may change behaviors at negative 3. We have to test the derivative and then see what happens as we go to the right of 4. So let's see how our derivative behaves, and then tell me how the original function behaves. Okay, can you see that? All right, so pick any number to the left of negative 3. Now, some tricks here. Any number to the left of negative 3, I'm going to pick something really big like negative 10. That's just my choice. Now you can stick negative 10 into your calculator, being really super careful that you use parentheses accordingly, or I'm just going to look at it in factored form. All I care about, I don't care about the value at negative 10, I just care if it's positive or negative. So if I put negative 10 into the factored form, notice if I put negative 10 in here, this is going to be 6 times negative 14 times negative 7. So 6 times negative 14 times negative 7 is going to be a positive number. Again, I don't care what the number is. All I'm trying to do is determine if the derivative is positive or negative to the left of negative 3. And anytime I pick a number to the left of negative 3, this factor is going to be negative, and that one's going to be negative. Thus, a positive times a negative will give me a positive derivative. So I know that this function is increasing to the left of negative 3. To the right, between negative 3 and 4, well, obviously if 0's in there, it's always a good choice. So I can put 0 in here, and I get 6 times negative 4 times positive 3, which is definitely a negative number. Or if we put 0 up into the original before I factored, we would see the output's negative 72. So you can stick it into it mentally. We don't need the value at these points. We will want the value at the critical numbers if in fact they're local maxes and mins, but right now we're just trying to determine whether or not the derivative is positive or negative. So I picked my favorite number between negative 3 and 4, which is 0. When I put 0 into either form of the derivative, the output is negative, so I know that the function is decreasing between negative 3 and 4. Pick my favorite number past 4. I'm just going to say 100. Any number to the right of 4. If I put any number to the right of 4, we're going to have 6 times a positive number times a positive number, because 100 minus 4 and 100 plus 3 are both positive. So the derivative is positive to the right of 4. My function's increasing. Right, so therefore, it's increasing, decreasing, and then it's increasing again. If it increases, then decrease. We have a local max at negative 3, and we're going to have a local min at 4. It says find all local extreme points. Not very often do we care exactly where they are. Often we care about the value or the actual coordinates of the points. So knowing that it's at negative 3 and 4 may not be enough. You just have to read your questions carefully. So at negative 3, the function at negative 3 is equal to, well, if we put negative 3 in here, I get, let's see, well, I get 145. That's a big number. You might just want to double check it, but it could very well be that big. So at negative 3, the function is negative 145. At positive 4, the function is, what did I get? Ooh, negative 198. So therefore, I would conclude f is increasing to the left of -3, and to the left of -3 is negative infinity to -3, and then it's also increasing to the right of 4, so 4 to infinity. F is decreasing between -3 and 4. F has a local maximum at the point -3, 145. The max value, even though the question didn't ask it, I'm going to tell you that the max value is 145. So if you see the word value, make sure you understand that that is only asking for the output. F has a local minimum at 4, -198, and the minimum value, I should say the local minimum value, and if I ask for the value, is -198. So it's everything we needed to know. All right, let's keep going. Let's try one that's a little bit trickier. Let's find all the local extreme points, determine where this function is increasing and decreasing. All right, so the first thing I need, it's f of x equals the cube root of x squared minus x. So we're going to take the derivative. I suggest anytime you have a radical, a function that has a radical, turn all radicals into fractional powers. The cube root is equivalent to x to the 1/3 power. So the derivative is 1/3. Leave what's inside alone, because this is the chain rule. Drop the power by 1 times the derivative of what's inside. Right, so I'm now going to put it in its fractional form all over the cube root, x squared minus x. Whew. Squared. Yeah, I should have left it like that. But anyway, okay. Now I'm going to leave it like this. Let me do this instead. I think this is easier. I like this better. X squared minus x to the 2/3. I think that's easier to look at. All right, so either way, both of those are equivalent. So now we want to know where is, so f prime equals 0 when the numerator equals 0, or when x equals 1/2. And the derivative is undefined when the denominator equals 0. 3 times x squared minus x to the 2/3 equals 0. But the only time the 3 is irrelevant, because we can divide the 3 out, and the only time something to the 2/3 equals 0 is when what's inside equals 0. So x times x minus 1 equals 0. So when x is equal to 0 or 1. So therefore my critical numbers are 1/2, 0, and 1. So it's getting a little bit more complicated. So I'm going to make a number line, and I'm going to look at this function's derivative before, between, and after these critical numbers. So we have, I'm going to write my function here. F of x is equal to the cube root of x squared minus x, and the derivative is equal to 2x minus 1 all over 3 times x squared minus x to the 2/3 power. And we found our critical numbers to be 0, 1/2, and 1. So this time we have to check 4 different places before, between, and after. So how does the derivative behave? And how does our original function behave? Now, again, don't make this harder than it has to be. Notice that the denominator of the derivative is always positive. No matter what we put in for x, we're going to square it first and then take the cube root. Or we could take the cube root and square it, but in the end, we're always going to be squaring the result of what's in the parentheses. So this denominator is only positive, always positive. So we really only have to check what's going on in the numerator. So for example, I'm going to try -1. How does the derivative behave at -1? Well, if I put -1 in here, I get -2 minus 1. The Numerator is negative, the denominator is positive, so the derivative is negative to the left of -1, and this function is decreasing to the left of -1. I picked my favorite number between 0 and 1/2. I'm going to say 1/4. So if I put 1/4 in here, I'm going to get 1/2 minus 1 in the numerator, which is negative. I don't even care what the value is. I just care if it's negative or positive. Denominator is always positive. So this is actually negative. The derivative is actually negative also between 0 and 1/2. So the function continues to decrease as it passes through 0. So even though 0 is a critical number, it is not a local max or min. Pick my favorite number between 1/2 and 1. Let's say 3/4. If I do 3/4 times 2 minus 1, the output's going to be 6/4, which is bigger than 1. Subtract 1. Derivative is positive. The original function's increasing. Pick my favorite number to the right of 1, like 100. 2 times 100 minus 1 is positive. Function's increasing. So it decreases. It continues to decrease as it passes through 0. It hits 1/2. It changes direction and now starts increasing. It passes through 1, even though 1's a critical number. It is not a local max or min. So therefore, f is decreasing on 0 to 1/2. F is increasing on 1/2. Whoops, that should be negative infinity. Be careful. Negative infinity to 1/2, because to the left of 1/2, to the right of 1/2, it's increasing. It is decreasing from 0 to 1/2, but it's also decreasing from negative infinity to 0, so don't lose that piece like I just did. Right? F has a local minimum at x equals 1/2. To find the value, we stick 1/2 into the original function. So go back up here, stick 1/2 into the original function, and the cube root of 1/2 squared minus 1/2 is the cube root of -1/4. The local minimum value is the cube root of -1/4. Local minimum point would be 1/2 cube root of -1/4. So again, just be really careful at what it's asking you. All right, so that's increasing and decreasing. Let's talk a little bit about concavity now. How does the derivative or derivatives tell us how a function's concavity behaves? Well, first we need to understand what concavity means. Concave up is whenever we have an arched up shape. Formally, a function is concave up when all tangent lines fall below the curve. So if you're not sure if a function's concave up at a point, draw a tangent line. The tangent line falls below the curve, it's concave up. Also, the slopes are increasing as we move left to right. And we mean increasing, not increasing in size per se, but increasing on the number line. So like over here, for example, let's look at over to the right here. We can see that it's getting steeper and steeper as we move to the right. But if we're over here on the left side, it's getting less and less steep, but on the number line, the slopes are increasing. So for example, if the slope here was -2, the slope here would be to the right of it, -1. This slope would be -1/2. We have a slope of 0 here. This would be a slope of about 1/2. This would be a slope of 1. So as we move left to right on the number line, the slopes are increasing. The slopes are moving left to right. So concave up and increasing looks like this. It's arched up and it increases like this. So it's increasing and all the tangent lines fall below the curve. Concave up and decreasing would be something like the square root function. So if we were to draw tangent lines, all our tangent lines would fall above that curve. Concave down. Well, concave down, if we start drawing tangent lines on a concave down curve, all our tangent lines will always fall above the curve. So all tangent lines fall above the curve. And when something's concave down, the slopes are decreasing as we move left to right. So the slopes are here, the slopes are positive and decreasing. Here the slopes are negative and decreasing. So concave down, whoops, and increasing. Oh no, I messed up this guy. Hold on, let's go back here. Nope, that's right. I messed this guy up. Holy Christmas. Let's go back to here. Not right, that's concave down. Concave up and increasing. Concave up and decreasing, my bad, would be this way. Concave up is arched up. So I apologize for that mistake. Don't do that. That's concave down and increasing. So concave up, it's arched up, and as we go left to right, we're decreasing. So concave down and increasing was what I drew previously. So as we go up, we go left to right, we're going up. There's my square root function behavior. Concave down and increasing. Concave down and decreasing, like this. So concave down is arched down, and decreasing as we go left to right, we're going to go down. All right, so this is probably one of my favorite tables that we'll be using. So I'm going to do a star here. So what we're concerned, or what we're interested in knowing, is where a function is increasing, where a function is decreasing, where a function is concave up, and where a function is concave down. Well, wherever a function is increasing, we know the derivatives are positive. And there's the back and forth relationship there. Wherever a derivative is positive, the original function is increasing. Wherever derivatives are negative, a function's decreasing. Wherever a function is decreasing, its derivatives are negative. Well, in those little informal definitions of concavity, wherever a function is concave up, its derivatives are increasing. And wherever its derivatives are increasing, the function is concave up. A function's concave down, wherever its derivatives are decreasing. And wherever it's decreasing, the original function is concave down. Right, so how does the second derivatives come into play? Well, there's nothing here, so we're just going to leave that, because a function can be increasing and positive, and it doesn't tell, my second derivative doesn't give me any information about the original function being increasing or the derivative being positive. But here, if a function's concave up and its derivatives are increasing, well, the derivative itself is a function, so if the derivatives are increasing, the second derivatives are positive, because the second derivative is the derivative of the derivative. So wherever a function's increasing, its second derivative is positive. Wherever the second derivative is positive, the first derivative is increasing. So wherever a function is concave up, its second derivatives are positive. Wherever its second derivatives are positive, the function's concave up. Can you see where we're going with this? All right. Likewise, wherever a function is decreasing, its derivative is negative. So wherever the derivative is decreasing, the second derivative is negative. Wherever the second derivative is negative, the derivative is decreasing. But where the derivative is decreasing, the original function is concave down. So wherever the second derivative is negative, the original function is concave down. Where a function changes from increasing to decreasing, or the derivative changes from positive to negative, we call these critical numbers. So we get the critical numbers when the first derivative changes sign. In the second derivative here, where it changed from increasing to decreasing, we call these inflection points. So an inflection point for a function is where a function changes concavity. So where the graph of the function changes concavity. So here, this function's concave up here. It's concave down here. So somewhere between here and here, it switches, and it looks like it switches about right there. So that would be an inflection point. And our goal is to use calculus to find the precise location of those inflection points. So to the right of the inflection point, we are concave down. It's arched down. To the left of the inflection point, we are concave up. So we want to find the precise location of those inflection points. And how do we do that? Well, we have a test for inflection points. Very similar to the first derivative test for local maxes and mins. We find where the second derivative is 0 or where the second derivative is undefined. These points are the only possible inflection points. We don't have a name for them, like we have critical numbers or where the first derivative is 0 or undefined. I just call them the possible inflection points. We determine the sign of the second derivative before, between, and after all possible inflection points. I abbreviate this PIPs, possible inflection points. If the second derivative changes sign at a possible inflection point, then that point is an actual inflection point. If the second derivative does not change sign at a possible inflection point, that point is not an actual inflection point. If the second derivative is positive on an interval, then the derivative is concave up on that interval. If the second derivative is negative on that interval, then the original function is concave down on, here I'll make it an I, on that interval. So it arches down. So where the second derivative is negative, the function's concave down. Now this is important because often we can't even tell from the graph, or when we use the trace or max minimum value on our calculator, it doesn't give us the precise locations, and our goal is to find these precise locations. So let's revisit 2x cubed minus 3x squared minus 72x plus 10. We already found the critical numbers. We found the derivative to be 6x squared minus 6x minus 72, and we found the critical numbers, previous example, to be -3 and 4. All right. Let's see if this function has inflection points. Well, to find inflection points, we're going to take the second derivative, which is 12x minus 6. We're going to set the second derivative equal to 0. It's not undefined anywhere because it's a linear function. So 1/2 is my possible inflection point. To test if it's an actual inflection point, we're going to do a number line, possible inflection point, and we're going to see how the second derivative behaves before and after 1/2. So the second derivative is going to determine the concavity. So I pick my favorite number to the left of 1/2. 0 is a great choice. Put 0 into the second derivative, and we see that it's negative. So the second derivative is negative to the left of 1/2, so the function is concave down to the left of 1/2. Pick my favorite derivative, my favorite point to the right of 1/2, 1. Stick it into the second derivative. The output is positive, so I know this function must be concave up to the right of 1/2. So therefore, f is concave down to the left of 1/2. So the left of 1/2 is -infinity to 1/2, and f is concave up to the right of 1/2. And if you draw this in your calculator, I'm just going to see if I have it. Do I have it in here? Let's do y equals, let's do 2, what was my original? 2x cubed minus 3x squared, and then it's going to be minus 72x. I'm going to see what our calculator tells us. minus 10. When I graph this guy, no, that doesn't work. Got to make sure you're in the right viewing rectangle. All right, so I'm going to go to zoom 6, always brings me back to the right. So we really can't, we just see a bunch of lines. So we could play with this, we could zoom out. We can kind of see something funky going on there, but we don't need our calculator to provide us with this information because I have, using calculus, everything I need to know. And F has an inflection point at 1/2. It's an actual inflection point. And if I want the value, let's see if my calculator will tell me the value. If I go second calculate, oops, second calculate, and I go value, I'm going to put in 1/2, and it's at negative 46.5. There's my actual inflection point. So I threw this into Desmos to see what the graph of this looks like. Right here, and here's the graph. So it's concave down, and you notice, look, this goes from negative 100 to 100. It goes, I'm going to look at my window. So we can see the arch down shape here. We can see the arched up shape here. And we have an inflection point about 1/2, somewhere about right there. So my inflection point is 1/2, negative 46.5. That would be very impossible to detect, or very difficult to detect, if we had to do this in other ways, like looking at the picture. So we want to be able to know the calculus. All right, let's take a look at another example. Let's look at x over x squared plus 1. So slightly more complicated. We want to find the intervals where f is increasing, decreasing, local max and minimum points, interval where it's concave up, concave down, and all inflection points. Well, notice it's arched up right here. It's arched down right here, so we're going to have an inflection point somewhere in there. And actually, it looks like it kind of arches up about right here, so there may be another inflection point over here and here. We can see that this is decreasing till it hits this point, and then increasing and then decreasing. So looking at the graph, we know we have some work to do. So we're going to first use our first derivative and find everything our first derivative tells us. So my original function is x over x squared plus 1. Let's see what the first derivative tells me. The first derivative says the derivative of the top times the bottom minus the top times the derivative of the bottom all over the bottom squared. I clean this up. It's x plus 1 minus 2x squared. It's going to be 1 minus x squared all over x squared plus 1 squared. Again, notice that the denominator is always positive. So it's not all that difficult when we're looking at critical numbers. All right, so now we have to find the critical numbers for this function. All right, so the derivative is equal to 0 when the numerator equals 0. And that happens when x is positive or negative 1. And the derivative is undefined when x squared plus 1 squared equals 0. But x squared plus 1 is positive for all x. So no critical numbers from the denominator. Because the denominator is never 0. So we're going to draw our number line. We only have to worry about the critical numbers, negative 1 and 1. So now we're going to stick our critical numbers into the derivative, or the numbers to the left and the right of the critical numbers into the derivative. All right, so we got my function right there. So if I pick my favorite number to the left of negative 1, I'm going to say like negative 10. I put negative 10 into the derivative right here. Notice the denominator is always positive. If I put negative 10 in here, I get 1 minus 100. The derivative is negative till it hits negative 1. So I can tell that the original function is decreasing to the left of negative 1. Pick my favorite number between negative 1 and 1. 0 is always a great choice. I put 0 into the derivative. Denominator is always positive. The numerator is going to be positive 1, so the function's increasing between negative 1 and 1. Pick my favorite number to the right of 1. I'll put in 10. I can put in 100. It doesn't matter. Any number to the right of 1. 1 minus any number to the right of 1 squared is going to be negative. So then the function decreases. So if we go back here, we can see that it changes direction at -1 and 1. So it decreases until it hits -1. It increases until it hits +1, and then decreases to the right of +1. So therefore, f is decreasing on, well, to the left of -1 would be -1, negative infinity to -1, and to the right of 1, 1 to infinity. We have f is increasing on -1 to 1. We have a local minimum, so we're going to have a minimum here. Local minimum at x equals -1. The minimum value would be the function defined at -1. So we're going to put -1 into the original function, which would be -1 over 2. The original function. And then we're going to have a local maximum because it goes up and then down. So we have a local maximum at 1. Local max at x equals 1. And the max value, remember if it says value, you want the output. And at 1, we stick 1 into the original function, and it would be 1 over 2. So it'd be 1/2. All right, so now we have to find the concavity and inflection points. All right, so my original function was x over x squared plus 1. The derivative was 1 minus x squared over x squared plus 1. Oh boy, this can get tricky quick, huh? All right, ready for this? So for the concavity, we need to see how the second derivative behaves. All right, so you want to be comfortable with taking derivatives. Ready? Second derivative, derivative of the top, times the bottom, minus the top, times the derivative of the bottom. The derivative of the bottom, bring the 2 out front, leave what's inside alone, drop the power by 1, times the derivative of what's inside. Sorry, I ran out of room. I'll clean that up in a minute. All over the bottom squared. Right. So let me rewrite this. This is -2x times x squared plus 1 squared minus 1 minus x squared. And then I have 2 times 2x. It's going to become 4x times x squared plus 1. There we go. All over the denominator squared. So x squared squared would be x to the 4th. All right, now we have to see where the second derivative equals 0. Now here's again where your factoring skills are going to come into play. So notice I didn't distribute anything in the numerator yet. Never distribute the denominator. It's already nice and factored for us. But I look at the numerator here, and before I distribute, I want to see if each of the 2 pieces has anything in common. Notice they both share a 2x, so I'm going to pull out, and they share the negative. I'm going to pull out the negative 2x, and they both have one factor of x squared plus 1. So if I pull the negative 2x and one of these x squared plus 1's out, all I'm left is x squared plus 1 from the first term. And then I'm going to, well, I pulled that negative out, so it's going to become plus 1 minus x squared. So that factor didn't go anywhere. I pulled the 2 and the x out of here, so I have a 2 left, and I brought that term out. So what I brought out is what they had in common. They had negative 2x in common, so I pulled out the negative in one of those factors of 2 here. I pulled out 1 x squared minus 1, and then what was left here was one of those out of the 2. This piece was still left, and then the 2 from there. And why does that help? Well, let me clean this up a little bit. We now have negative 2x, x squared plus 1, and then x squared plus 1 plus x minus x squared times 2 is all going to give me negative x squared plus 3. In that set of parentheses, x squared plus 1 to the 4th. Now, again, this denominator is always positive, so to find our possible inflection points, we're going to set just the numerator equal to 0. If there was the chance, like if this was minus instead, we would have to see where the denominator was undefined. But this denominator is never 0. It's always positive. So that's very helpful. So we only have to look at when the numerator is 0. Okay, well, this is 0 when x equals 0. This is never 0 because x squared plus 1 is always positive, right? And then here, this is 0. Well, we set it equal to 0. We get negative x squared plus 3 equals 0. X is equal to the positive or negative square root of 3. So subtract 3 from both sides, multiply by negative 1. The square root of x squared, don't forget the positive negative option. Right. Note, x squared plus 1 to the 4th is never 0. So no critical numbers come from the fact that the second derivative is undefined. So therefore, my possible inflection points are 0, negative square root of 3, and positive square root of 3. So now we have to check how the second derivative behaves before, between, and after these points. So here's my second derivative. I'll rewrite it. So my second derivative is negative 2x, x squared plus 1, negative x squared plus 3, all over x squared plus 1 to the 4th, keeping in mind the denominator is always positive, so we really are only checking how the numerator behaves. So this is a true die-hard calculus problem. Right. So we want to check the second derivative, and then you can tell me about the original function. Right, so my favorite number to the left of the negative square root of 3, I don't know, I'm going to do negative 10. If I put negative 10 in here, this becomes positive. This is always positive. X squared plus 1 is always positive. We put negative 10 in here. Make sure you square the negative 10 first and then take the opposite. So negative 10 squared would be positive 100. With the negative, it'd be negative 100. So this is going to be negative. So it'd be positive, positive, negative. My second derivative is negative to the left of negative square root of 3. So therefore, the original function is concave down to the left of negative square root of 3. Pick your favorite number between 0 and negative square root of 3. For simplicity, I'm just going to do negative 1. If I put negative 1 in here, positive, that's always positive. Well, that'd be negative 1 plus 3, positive. So this function is concave up between negative square root of 3 and 0. Favorite number between 1 and 0 and the square root of 3, I'll do positive 1. If I put positive 1 in here, this piece is negative 2. This is going to be positive 2, so it's going to be negative. So 0 is also an inflection point, so far 2 out of the 3 are. Concave down. And then to the right is square root of 3. I'm just going to do positive 10, negative, positive, negative. That's going to be positive. Concave up. So therefore, we have actual inflection points at. So therefore, we say F is concave down on, well, to the left of negative square root of 3, so negative infinity to negative square root of 3. And it's also concave down between 0 and the square root of 3. F is concave up on, well, between negative square root of 3 and 0, and to the right of the square root of 3. And we have inflection points at negative square root of 3, 0, square root of 3. Woohoo! Quite the calculus problem. Bet your hand's hurting a little bit now. All right, so one more thing. Let's just remind ourselves what we have so far. We use the first derivatives to find local maximums and local minimums to determine where the function is increasing and decreasing. If the derivative changes sign from positive to negative at a critical number, then the function changes from increasing to decreasing at that critical number, and we have a local maximum at that critical number. If the derivative changes from negative to positive at a critical number, then the function changes from decreasing to increasing at that critical number, and we have a local minimum there. We use the second derivatives to check concavity. We find for possible inflection points by setting the second derivative equal to 0 or determining where the second derivative is undefined. If the second derivative changes sign at a possible inflection point, then there's an actual inflection point there. If a second derivative is positive on an interval, the function's concave up on that interval. If the second derivative is negative on that interval, the function's concave down on that interval. All right, there's one more test. It's called the second derivative test for local maximum and minimums. Now note back here, we used the second derivative to check concavity, but it's not called the second derivative test. The second derivative test actually checks for local max and mins, and it's slightly different. So, what does the second derivative test say? Well, the second derivative test says, let's find a critical number for a function. Critical number is the derivative equals 0 at that point, or the derivative, oh, I messed that up, equals 0 at that point, or the derivative is undefined. When we stick that critical number into the second derivative, if the second derivative at that critical number is positive, then f has a local, ready for this, local minimum at C. So what's happening is C is a critical number, so it's a local, it could be a local max or min, but if it's concave up at that point, so if it's concave up and the derivative is 0, it's going to be a local min. If we stick a critical number into the second derivative and the output is negative, then f has a local maximum at C. So if the second derivative is negative and it's concave down, well, if it's concave down and the derivative is 0, it must be a local max. If the second derivative at a critical number is 0, this test is inconclusive and must go back to the first derivative test. So this is just an option. This is so we don't have to use that number line. Unless the second derivative is 0 at a critical number, then we would have to use the number line. So let's just revisit this guy and see how this could have been a little bit easier. So the first derivative was 6x squared minus 6x minus 72, not undefined anywhere, but we did find the critical numbers previously to be -3 and 4. So previously we drew the number line, but the second derivative test says, you know what, don't worry about that number line. Let's take the second derivative, 12x minus 6, and let's check the critical numbers at the second derivative. If we stick -3 into the second derivative, we get -36 minus 6. I don't care what the value is, but I do notice that it's negative. So the second derivative at the critical number -3 is negative. So therefore, f has a local max at x equals -3. We did this previously using the number line. The second derivative at 4 would be 12 times 4, which is 48 minus 6. I don't really care about the value. I only care that it's positive. So because the second derivative is positive at that point, it must be concave up at that point. So second derivative is positive, saying it's concave up, so it must be a local min. So f has a local min at x equals 4. So sometimes, again, this test is inconclusive. In this case, it was not inconclusive, but if we stuck a critical number into the second derivative and the output was 0, the test would be inconclusive, and we would have to use the first derivative test. So make sure that you can use both tests. All right, I know this was a long one. I appreciate your patience, and good luck in section 4.3.